Our topic for today's discussion is coupled circuits. Before we discuss the concept of coupled circuit, let us review few basic points which you have studied in your earlier classes or previous semester. Suppose a coil is there having n number of turns with a self-inductance of L henries. Let us send an alternating current of I amperes through the coil. Now, there will be an EMF induced in the coil because of change of current through the coil or because of change of flux associated with the coil. When we express the induced EMF in the coil because of change of current, you know that induced EMF is given by L di by dt. The same induced EMF can also be expressed in terms of the change of flux, which is N d phi by dt. This particular EMF is called self EMF because of the reason the current is its current. The current flowing through the coil is its current. Similarly, the flux is its flux. The flux linked with the coil is its flux. Accordingly, this self-inductance L can be expressed mathematically in terms of N, in terms of phi, in terms of I, like this. L is equal to N d phi by di. The same self-inductance can be generalized in terms of phi and I as L is equal to N phi by I, as flux and current we are considering as linear variables. Hence, the point here is a coil will always have EMF associated with it whenever current changes through the coil or whenever the flux linked with the coil changes. Now, let us consider an interesting case. A coil is there. Imagine the self-inductance of the coil is L1 henries. It has N1 number of turns. I am sending a current of I1 amperes through it. As you know, whenever current is passed through a coil, there is a magnetic field around the coil. I am considering this magnetic flux as phi 1. Basing on the discussion we had just now, this particular coil self EMF, I am representing it as V1, it is L1 di1 by dt, or this is also equal to N1 d phi 1 by dt. Imagine I brought another coil into the vicinity, of this magnetic flux like this. A coil is brought inside. But the point you need to observe here is there is no electrical connectivity between these two coils. This coil is separated from the coil number 1 by some distance. Still, this coil number 2, which is having a self-inductance of L2 henries, having N2 number of turns, is within the magnetic field generated by coil number 1. Let us assume the coil number 2 is having a part of the flux generated by coil number 1. Let us denote phi 12 as the flux linking the coil number 2 because of the total flux generated around coil number 1, which means out of phi 1, phi 12 is a part of the flux linking the coil number 2. Now we have a situation where phi 12 is also changing because of change of phi 1. According to Faraday's laws of electromagnetic induction, whenever flux linking a coil changes, EMF will be induced in the coil. Accordingly, now another EMF you are observing in the situation, and that EMF is induced in coil number 2, and that EMF we are calling it as mutual induced EMF. Before we write expression for this mutual EMF, the concept you need to understand at this stage is when two coils are linked magnetically because of flux generated in one of the coils, there are two types of EMFs produced. First EMF is self-induced EMF in coil number 1, and the other EMF is mutual EMF in coil number 2. And this EMF induced in coil number 2 we can express in terms of the number of turns of coil number 2 as N2 d phi 12 by dt. This is one way of expressing the mutual EMF in coil number 2. Along with this, EMF, along with this way of expressing the mutual EMF. There is another way of representing the mutual EMF as M di1 by dt. Here, two important aspects you need to understand. The first one is this EMF in coil number 2 is because of change of current in coil number 1. This current I1 is given to coil number 1. And the second point is this induced EMF is depending on a constant called M. M is known as mutual inductance between the two coils. Hence, mutual EMF induced in coil number 2 is depending on a constant called mutual inductance between the two coils, and in the representation of coupled circuits we always represent M between the two coils like this. Whenever we show M between the two coils, it implies that there will always be mutual EMF in the other coil whenever current in one of the coils is changed. This is the mutual inductance with which the coupled circuit is able to induce EMF in the other coil. Hence, M di1 by dt, as we already discussed, this is a mutual EMF can also be represented in terms of number of turns. Once we equate these two expressions, from this we can write M is equal to N2 d phi 12 by di1, or we can generalize this as N2 phi 12 by I1. So let us repeat this in terms of sending current through the other coil. Now, whatever the concept we discussed till now, let us review it in terms of discussing the entire thing by sending current through coil number 2. So, I have considered a magnetic coupled circuit. How can I say this is a magnetic coupled circuit? They are not electrically connected, that is one thing. Second, I am representing M between the two coils, which implies that there is mutual inductance between the two coils, with which the other coil gets mutual EMF whenever current in the other coil changes. Now what I am doing is, this is having L1 self-inductance, number of turns N1, L2 is the self-inductance of coil number 2, N2 number of turns of the coil number 2. I am sending a current of I2, alternating current I2 through L2. Now, which coil will have self-induced EMF, obviously coil number 2 will have self-induced EMF. Reason is the current is its current. The current is flowing through coil number 2, hence self EMF is always in coil number 2. And because of this current, magnetic flux is developed around coil number 2, and I am denoting that as phi 2. And a part of this phi 2 is linking coil number 1, and that part of the flux I am denoting it as phi 2 1. At this stage, you need to understand the suffixes notation I am representing. Suffix phi 2 1 indicate 2 is the coil through which you are sending the current, and the main flux developed around coil number 2 is phi 2, and a part of this phi 2 is linking coil number 1. So the second suffix we are representing is the other coil where the main flux is linking. If you recollect the previous discussion, in the previous discussion I used phi 1 2 because phi 1 is the main flux developed around coil number 1, and the second suffix 2 there, it represents the second coil where the mutual EMF is induced. Hence, in this case, self EMF is developed in coil number 2, hence I must represent V2. V2 is self EMF. And mutual EMF in the other coil obviously is V1, which is mutual EMF. Let us represent V2 and V1 basing on the notations we discussed. Now, see how am I writing the self EMF of coil 2 in this case. It has N2 number of turns. It has flux associated with it, which is phi 1 2 by dt. It can also be expressed in terms of self-inductance. L2, the current flowing through it is I2 di2 by dt. Now V1, it is a mutual EMF. Mutual EMF in coil number 1 in terms of number of turns. It has N1 number of turns. What is the flux associated with the coil number 1? It is d phi 2 1 by dt. It can also be expressed in terms of the mutual inductance as M di 2 by dt, because the current is passed through coil number 2. Here this flux developed in coil number 2 is not phi 1 2. The flux developed in coil number 2 because of the current flowing through it is phi 2. Phi 2 is the main flux which is linking the coil number 2. Out of this phi 2, phi 2 1 is linking the coil number 1. That's why this particular EMF is mutual EMF and this particular EMF is self EMF. Now from this we can write the mutual inductance M is equal to N1 phi 2 1 by I2, or M is equal to N2 phi 2 1 by I2. So the first case, when we refer, we have written V2 is equal to M di1 by dt. First case we have considered. We also have written N2 d phi 1 2 by dt. Accordingly, M is equal to N2 phi 1 2 by I1. In the second case, when we analyzed the coupled circuit, the mutual EMF we got in coil number 1, which is M di2 by dt, or this is N1 d phi 2 1 by dt. Accordingly, M from this is N1 d or phi 2 1 by I2. So at this stage, any coupled circuit magnetically, that is flux developed in one coil linking the other coil, we have way of expressing the mutual inductance between the coils either in terms of N2 phi 1 2 by I1 or in terms of N1 phi 2 1 by I2. Now I am going to introduce what is meant by coefficient of coupling between the coils of a magnetically coupled circuit. Imagine a flux of phi 1 developed around coil number 1. A part of this is linking coil number 2, and that is phi 1 2. What is meant by a part of the flux? For example, 100 milliwebers is the flux phi 1. A part of this means 60%, 30%, 40%, like this. That means always that part of the flux is less than 1. like 40% means 0.451, 60% means 0.651. Hence, I can always write 512 is a part of 51 where that part which is less than unity, that part is called coefficient of coupling, and this coefficient of coupling is represented by K. This always indicate when we see this specification in a coupled circuit, what we can understand from that specification is how intensely the linking is taking place between the two coils of a coupled circuit. A simple example is, suppose you have two coupled circuits. The first coupled circuit has a K value 0.9. The second coupled circuit has a K value 0.7. By looking at these two specifications, one can easily understand that the first coupled circuit has more magnetic coupling because more percentage of main flux is linking the other coil. Coming to the second coupled circuit, which has K value as 0.7, it implies that relatively less magnetic coupling is existing between the coils of the coupled circuit. The same K can be expressed in a different way also. For example, just now we discussed when coil number 2 is given current, the main flux developed around coil number 2 is phi 2, and a part of this flux linking the first coil, we denoted it as phi 2 1. Accordingly, I can also write phi 2 1 is K times phi 2. Phi 2 is the main flux developed around coil number 2. A part of this is linking coil number 1. Accordingly, we can express phi 2 1 like this. This is what coefficient of coupling means. It is a fraction of main flux linking the other coil when current through one of the coils is changed. Now, let us try to establish relationship among self-inductances, mutual inductance, and coefficient of coupling with the mathematical expressions we discussed till now. I am trying to get the relationship among M, L1, L2, K. For this, let us first consider the expression we had for M. One of the expressions we had for M. While considering coil number 1 as the main coil, coil number 2 as the coil in which mutual EMF is existing, we already discussed that M can be expressed as N2 phi 1 2 by I1. Similarly, when coil number 2 is considered as the main coil and coil number 1 is considered as the coil in which mutual EMF is there, we already discussed that M can be written as N1 phi 21 by I2. Suppose I multiply these two, we get M square is equal to N2 phi 12 by I1 into N1 phi 21 by I2, which is N1 N2 phi 12 phi 21 by I1 I2. Let us see how to expand it further. So what I got is M is equal to N1 N2 phi 12 into phi 21. Phi 12. What is phi 12? It is K times phi 1, a part of the main flux linking the other coil is in terms of K. Similarly, what is phi 21? It is K times phi 2. I am going to substitute these two in place of phi 12 and in place of phi 21. Accordingly, we get this is K square N1 phi 1 by I1 into N2 phi 2 by I2. Now recollect how we started our today's class. I started initially with the concept of self-inductance, self-induced EMF. The self-induced EMF in any coil can be represented in terms of L di by dt, or it can also be represented in terms of N d phi by dt. Accordingly, this L is equal to N phi by I. Whenever we represent the self-EMF, self-inductance, we can represent it as N phi by I. Accordingly, what we are supposed to do is this N1 phi 1 by I1. In this place, I am substituting L1, self-inductance of coil number 1. In place of N2 phi 2 by I2, I am substituting L2. So, we got the relationship among M, K, L1, L2 as M is equal to K root L1 L2. This is a useful relationship which we will be effectively utilizing whenever we are analyzing any coupled circuit. M is equal to K root L1 L2. Hence, till now we discussed very few basics of coupled circuit before we enter into the actual main topic of how to analyze a magnetically coupled circuit. So before we start discussing the analysis of magnetic coupled circuit, the essence of the basics what we discussed today, it is nothing but every magnetic coupled circuit has two types of EMFs. One is self-induced EMF and the other one is mutual induced EMF. There will always be mutual inductance between the coils of magnetic coupled circuit. The mutual inductance is the ability of a magnetic coupled circuit to induce EMF in other coil whenever the main coil flux is changing or whenever the main coil's current is changing. The fraction of the main flux linking the other coil is called coefficient of coupling. Now, we start the topic how to analyze a magnetic coupled circuit, and this analysis is very useful for every branch student of engineering, because irrespective of the branch of engineering, this magnetic coupled circuit is an important topic which is having its various applications in various domains. For example, when you consider a transformer, all of you might have seen or might have heard about a transformer which transfers power from one primary winding to the other winding. That transfer of power from one end to the other end is basing on the principle of mutually induced EMF. And there are many coupled circuits which are used even in tuning circuits, electronic tuning circuits, where the concept of mutual induced EMF and coupled circuits are extensively used. Now let us go to the concept of how to analyze a coupled circuit. There are three stages in dealing with analysis of a coupled circuit. I will explain those three stages in terms of giving a sequential number, so that later when we deal with the problems, you will be in a position to map the analysis very easily to the sequence I am discussing in this topic. This particular representation, what you are seeing here, is a core. A core, the winding arrangement of the coupled circuit is always made on the core. Imagine A coupled circuit is shown like this. There are two coils, coil number 1, coil number 2, both are not electrically coupled, they are magnetically coupled by means of core on which the windings are arranged. Think a current of I1 is passed through this coil and a flux of phi 1 is generated from main coil. In the analysis, the first step you need to identify is what is the direction of the main flux developed in the core of the coupled circuit. Now, I am going to explain, which you have already studied in your childhood classes, a rule called right hand rule or right hand gripping rule. The meaning of the essence of this right hand gripping rule is, take the coil in your right hand covering the core such that the fingers enclosed are in the direction of current, which means this is the direction of the current in the main coil. I am holding this core in such a way that my right hand fingers enclosed are matching with the direction of current. Once I do it, the thumb projected gives the direction of main flux developed in the core. Accordingly, I need to mark the flux direction upwards. See this, I marked flux direction upwards because of the reason, when I take the core in my right hand, the fingers are enclosed. Now the direction of current is matching with the direction of my enclosed fingers, and the flux direction is shown upwards in the direction of thumb projected. Now, this flux see its direction, see its direction. This flux is moving in the clockwise direction. So at this stage, I have a main flux, and that main flux is moving in the clockwise direction in the core. Now listen carefully. Imagine this particular flux In the other coil, a current of I2 amperes is sent by me separately in coil number 2. Now, let us try to identify what is the direction of flux in coil number 2 because of current I2. Now, this particular current direction is like this. Again, I am applying right hand gripping rule to coil number 2. When I do this, my right hand fingers enclosed, they are in the direction of current, and thumb projected is giving a direction of flux. Hence, which direction I need to mark the flux in coil number 2? Obviously, that direction of the flux is downwards. The flux developed in coil number 2, if we denote it as phi 2, this phi 2 is matching with the direction of phi 1. You may think that phi 2 is downwards, phi 1 is upwards. How can phi 2 is matching with the direction of phi 1? The answer is, if you extend the direction of this, see this, it is also moving in the clockwise direction. Green color flux I marked phi 1 is in the clockwise direction. Red color flux phi 2 also is in the clockwise direction. Both the fluxes are in the same direction, or both the fluxes are aiding each other or helping each other. That means there could be a situation in the coupled circuits in which the main flux or the fluxes in both the coils are aiding each other or in the same direction. Now let us consider another case. Before we draw the conclusions, you need to clearly understand various cases. In case number 1, what I showed was the two fluxes are helping each other. They are in the same direction. This entire thing we have analyzed and we drawn the conclusion that these two fluxes are in the same direction. Now I show another case, and let us identify what happens in this particular case. This is a core. This is winding number 1. This is winding number 2. But I am changing a little bit the directions of currents. Current I1 is like this only, but current I2 I marked like this. Now my question is, I want all of you to mark the directions of fluxes in coil number 1 and in coil number 2 and also to identify whether the fluxes in both the coils are in the same direction or in opposite direction. Now, how to draw our conclusion for this question? As I already explained, coil number 1, this is the direction of given current. I am applying right hand gripping rule. Once we take the coil number 1 core part in our right hand, fingers enclosing the direction of current, the thumb projected is giving the direction of flux in coil number 1, and this is moving like this. Now let us take the coil number 2. Coil number 2 current is like this. So when you take a coil number 2 in your right hand, what is the direction of the thumb projected? Now if you see, the fingers enclosed in the direction of current, the thumb projected is giving the direction of flux, and this particular flux direction, if you see in the core, it is moving exactly opposite to the flux of coil number 1. Hence, in this case, the flux in coil number 2 is opposing the flux developed in coil number 1. Hence, the conclusion is, in a coupled circuit, there can be fluxes helping each other, there can be fluxes opposing each other. This is the first basic concept you need to understand in the analysis of coupled circuits.